Hey everyone, welcome back to week 8 of my series where I learn ML through an optimization perspective. So if you've been following along, we've been working through the Boyd Convex optimization textbook. And so this week I finished section 3.1, convex functions. And honestly, this is one of those foundational sections where you just have to take it really slowly and really make sure you understand it. So anyways, chapter 3 is all about convexity of functions. So we just spent a bunch of time in chapter 2 learning about the convexity of sets. So now we're doing convexity of functions. So I was really eager to get on with it basically and just learn it. All right, so let's get into it. So just starting with the definition, a function f from R of n to R is convex if the domain of f is a convex set. And for all x and y in the domain, for some theta that's between 0 and 1, we have this inequality here. So let's see what this means geometrically. So the left-hand side, a combination of x and y, where x and y are the domain. So this, if you remember, this is a line between x and y. So the left side is just a function evaluated alongside the line between x and y. On the other hand, the right side is the weighted average of the outputs. So it's a linear combination of f of x and f of y. So geometrically, that's the point on the chord connecting x f of x and y f of y. So in other words, on the graph here, we can see, this is where x is, and this is where y is. And we take some combination of x and y, so that's any point, between these 2 points. And the left side says, just take the function of those linear combination. So for example, halfway in between, we take the function value and we're here. On the other hand, if we take the same linear combination of the outputs, we would be here on the chord. And so what this inequality is saying is that the function applies to the linear combination of input, it must be lower than or equal to the same linear combination of the output. And you just see that basic fact here. And so this sort of characterizes a convex function. So one elegant fact worth noting is that affine functions always have equality on this condition rather than inequality. So they're simultaneously convex and concave. And it turns out that that's not a coincidence. Any function that is both convex and concave must also be affine. So now is where things get really interesting. If the function is differentiable, we get a much more powerful characterization. So in this characterization, which is called the first order condition, f is convex if and only if the domain of x is convex, and for all x and y in that domain, we have the following inequality. Okay, so let's make sense of this. First, let's notice that it resembles something of the form of the first order Taylor approximation. So let's write that down. So the first order Taylor approximation, if you remember from your calculus, is given by this equation. So the output f of y is approximately equal to f of x with this slope at point x multiplied by the difference. So in this case, this is only in one-dimensional space, meaning that the input space is only one-dimensional. But if the input space goes to n-dimensional, it generalizes to the gradient, like this. All right, here's the n-dimensional gradient. You can see if the dimension of x is 1, then we obviously recover the familiar approximation from your calculus class. So with the generalized Taylor approximation in mind, let's go back to the inequality. So what the first order condition is really saying is that the tangent plane is always a global underestimator of the function, not just locally everywhere. So in other words, if if f is convex, then the tangent plane, in this case, is one-dimensional, but of course, you can imagine a third dimension in this example. It's always a global underestimator of the function. So this blue line is f of y, and the red dotted line, is this expression here. So I want to really let that sink in for a second. You're at some point x, and you look at the local slope here, and for a convex function, that local information just around this point here gives you a guarantee about the entire function. Everything else on that function is at least as high as your tangent line or tangent plane predicts. So this is the most basic but most profound insight in convex optimization, is that local behavior provides guarantees about global behavior. And there's an immediate result that follows, is that when the gradient is 0, then you just plug in 0 here, and you get that f of y is greater than f of x for all y in the domain of f. So what this means is that when the gradient is 0, then you found some point f of x, which is the global minimum of the function. Every other point y in the domain of f must be greater than or equal to this point f of x. So this is the essential reason why convex optimization is well studied and well understood. It's because we have these properties here. This doesn't hold for non-convex optimization, where you don't have these sorts of guarantees. So before we continue to the second order condition, let's first check and think about why the first order condition is true. In other words, let's think about the proof. So I'll go in the forward direction just for now. So concretely, what we want to show is that if f is convex, then for all x and y in the domain of f, this inequality holds true. So how do we show that convexity of f implies this inequality? We have to start with the definition of convexity, which is, comes from above here. So I'll start in the one-dimensional case, so n equals 1. So the idea is relatively straightforward. In the one-dimensional case, we want to recover the definition of a derivative. Okay, so just doing some algebra and dividing everything by t, we have this expression here. And then just taking the limit here, you can show that this is the definition of a derivative, but with just some y minus x offset. So why is this true? Well, you just let h be equal to t times y minus x, and then you solve for t here, and you see that y minus x goes up to the numerator, and you have the definition of the derivative. Okay, so we've just shown that the first order condition in the forward direction is true for the one-dimensional case. But what about the n-dimensional case? How do we generalize to n dimensions? Well, the book I use a very clever trick, so I'd like to just share that with you guys. So here's the idea. We just showed that this inequality holds true for n equals 1. But notice that, the function f takes an n-dimensional vector, so an r-van, and then outputs a one-dimensional scalar. So what if we define some function g of t such that the input is the output of the function f? So in other words, g of t takes a real number and then outputs a real number as well. This way, we're still in the space of real numbers. So let's do that by defining this function here. And then we can also calculate its derivative, which is just this expression here by the chain rule. But notice that g of t is simply just the altitude or the height, or the function of the linear combination of points between y and x. In other words, g of t parameters by t is simply just a one-dimensional line. And so since f is convex, we know that g of t must also be convex as well. Okay, then we do this trick where we set t equals 0 and we just plug that into the g equation and we get this. So what does each term mean? Well, g of 1 is you just take t equals 1, and when t equals 1, this expression goes to 0 and you're just left with f of y. Likewise for g of 0 and g prime of 0. And so you plug all this in and you get the first order condition, exactly what we want. And we're finished with the argument. So just to recap how that worked is we first showed that this property holds for one-dimensional functions, meaning it takes a one-dimensional input and outputs a one-dimensional output. Okay, then we said, okay, if we can define a one-dimensional function whose input is a generalized function, then maybe we can use our previous knowledge about one-dimensional functions to derive some interesting properties, or the property in this case that we want, of the n-dimensional function. So we did that a little bit cleverly, and we arrived at our conclusion. All right, so now let's talk about the second order conditions. So if we have the second derivative available from function f, the characterization is slightly different. So it uses what's called the Hessian matrix. So let me first explain what that is first. So the Hessian is an n by n matrix, where the ith entry and the ith jth entry is the second derivative, of the ith component first and then the jth component second. So just writing out explicitly, the Hessian is just a matrix defined as follows. So for smooth functions, the matrix is symmetric. So the order of partial differentiation doesn't matter in this case. So that means that the Hessian matrix is always symmetric. So from spectral theorem, we know this means that it has real eigenvalues and orthogonal eigenvectors. Now let's review where does the Hessian naturally appear. So you might have guessed it, but the Taylor expansion makes it a second appearance. So let's look at something familiar first. So when n equals 1, or the one-dimensional case, we should be familiar with the second order Taylor approximation here. And so obviously this is the first order term we just talked about. But if you want to do the second order approximation, of course you need the second term here. So the first term captures the slope. On the other hand, the second term covers the curvature, whether it's curved upwards or curved downwards. Okay, and then we can generalize this to n dimensions. So that means that x and y are n-dimensional, and we see our familiar, first order approximation, but we also see the second order approximation. And look at that, our Hessian appears in the second order approximation. So let's bring this term over here and let's look at it more closely. So just to be super clear, we let some vector in n dimensions v be the difference, and so we can write the second order as this. So what this is saying is that for some vector v, this expression gives you the curvature of the function f pointing in that direction v. So this is where our intuition kicks in. You might say if for any direction v, if you choose v to be anything, at least in the domain of f, then if for any vector or direction v, this expression is positive. In other words, the curvature in the direction of v is positive, then it must be the case that f must be convex. The reason is that the curvature is upward in any direction, so the function must look like a bowl, right? But hold on a second. Remember, this is exactly the definition of positive semi-definite matrices. If we say that the Hessian must be greater than or equal to 0 under the generalized inequality, this is the same as the Hessian being positive semi-definite. And so the definition of positive indefinite is that, you know, this expression here must be greater than or equal to 0 for all vectors or directions v. Okay, great. So now we've arrived exactly at our second order condition for convexity. So f is convex if and only if the domain of f is convex and the Hessian is a positive semi-definite. Okay, I'm not going to prove it because it's a little bit more involved, but let's instead dive deeper into more of the linear algebra. In particular, I hinted at earlier about eigenvectors and eigenvalues, so let's see how the Hessian and convexity is related to eigenvalues and eigenvectors. So in particular, since the Hessian is symmetric, we can decompose it as, you know, the eigenvalues and eigenvectors. So Q is the orthogonal matrix of eigenvectors, and this capital lambda is the diagonal matrix of the eigenvalues. So in this case, the eigenvectors are the principal directions of curvature. They form a natural coordinate system aligned with the geometry of f at x. And the eigenvalues tell you the curvature magnitude in each of these directions. To see what I mean a little bit better, consider this diagram I made. So here, Q1 is the eigenvector pointed in this direction. In this case, this is the first principal component direction. We can see that lambda is 2 because in this case, f is really sloping along in the x1 direction. On the other hand, it's not really sloping so much in the x2 direction. And so that's why lambda 2 is, pointing in the second principal direction is, only half. And notice that, Q1 and Q2 are orthogonal with each other. That's important. To see this concretely, plug the decomposition into the quadratic form. And so let's first let W equals Q transpose V, which is just V expressed in the eigenvector coordinate system. So we do that, we just plug in, this expression here for the Hessian. We substitute W in here, and we can rewrite this as follows. So for this sum to be non-negative for every direction V and for all W, you need every eigenvalue, these lambdas here, to be non-negative. So that's the spectral interpretation of positive semi-definite, no negative eigenvalues. So in other words, we know from linear algebra, but in terms of convexity, if the Hessian is a semi-definite, that means that all the eigenvalues must be greater than or equal to 0. And so, of course, that means that it must be convex, because the curvature in any direction must be positive. So just taking a step back for a moment, why do I think this section matters for ML theory? Well, a lot of the time when we talk about ML models, especially in the modern, environment, we're talking about optimization problems in the non-convex lost surfaces. This is a big story about, recent developments and so forth. Lots of local minimum, saddle points, and real geometry. That's non-convex optimization. But I think that makes understanding convexity actually more important, not less. The reason is that because you know what convexity gives you, the theoretical guarantees like global minimum or gradient information or tangent planes or whatever, you understand exactly what you're giving up when you move to non-convex settings. So I believe it sharpens your intuition and makes you understand the landscape a little bit better, maybe a lot better in some cases. Also, that's perhaps maybe even besides the point. I mean, a lot of classical ML methods, logistic regression, SVM, lasso, they have convex objectives, and those are still very much relevant. And they're actually, part of the building blocks of modern methods. So this convex optimization, directly explains why those methods are well behaved. All right, so that's section 3.1. So next week I'll be moving on to the rest of chapter 3, like operations that preserve convexity, like composition rules and other things. So it should be pretty interesting because it builds a toolkit for recognizing convexity in the wild, without having to go back to the, most fundamental definition every time. So, as always, I'm just a person studying this stuff and sharing as I go. If something seems off, let me know in the comments. So with that in mind, I'll see you next week.